In this video we're going to be looking at composite functions, which is a topic that most students find quite tricky, but with a bit of practice it can become quite a reasonable topic to attempt. So let's start out small. We're going to consider the functions with rules f of x equals the square root of x, which we're going to do in blue, and we have the function with the rule g of x equals 6x plus 4, which we're going to do in green from now on. For part A we're going to find the value of f of g of 2, and for part B we're going to find the value of g of f of 9. And we're going to demonstrate two slightly different methods to evaluate composite functions with a numeric value in them. And you can see the difference and the similarities, and then choose if you like one over the other when you're attempting similar problems like these in the future. So for part A we're going to start by just looking at the g of 2 part, which means we're going to evaluate the function g when x is 2. And to do that we're going to do 6 times x, but x is being replaced by 2, so we'll have 6 times 2 plus 4, and 6 times 2 is 12 plus 4 gives 16. Next we're going to evaluate f with g of 2 substituted into it. However, that's equal to f of, and g of 2 is found to be 16, so that will equal the square root of 16, which is simply equal to 4. So that is the answer to part A of this question. For part B we're going to do a slightly different method. So we're actually going to find the full rule for g of f of x first. So the function g of f of x is equal to the function g, which is 6 times x, but wherever there's an x we're going to replace that by the rule of f of x, which is simply the square root of x. So we have 6 times the square root of x, and we've still got plus 4, which completes the function g of x. So now that we have a rule for g of f of x, g of f of 9 is simply going to be equal to 6 times the square root of 9 plus 4, and this is simply equal to 6 times the square root of 9 is the same as 6 times 3 plus 4. So we have 6 times 3 is 18 plus 4, which is simply equal to 22. So that is the answer for part B of this question. Now we're going to go a little bit further with our ideas around composite functions. So we still have the same f of x equals the square root of x, which is going to be done in blue, and g of x hasn't changed, it's still 6x plus 4, which is in green. And now in red we're going to consider the composite function f of g of x, and for part C we want to find its domain, and for part D we want to find the range of f of g of x. Now it's not essential to do what we're going to do next, but often it's useful to sketch the graphs of your two individual functions f and g, and then think about what the composition of f and g is going to be. So we're going to start off here with a set of axes representing x and y, and in blue we're going to sketch the square root graph. So that's f of x, and it starts at 0, 0, and that's a coloured in dot. So that means it has a domain of 0 with a square bracket to infinity, and a range, and that's also 0 to infinity, and we can see that from the graph. Next we're going to consider the g of x function. So this is x and its y value, and g of x is a straight line 6x plus 4, so it's going to have quite a steep gradient. It's going to have a y-intercept there of 0, 4, and its x-intercept, if you solve that equal to 0, is going to be minus 2 on 3, 0, and it at the moment has a domain of all real numbers and a range of all real numbers as well. So all real numbers can go into the function, and all real numbers come out as y values of that straight line. So if we want to find the domain of f of g of x, what we need to do is think about all of the values of x that we can plug into g of x, which is our green function, that give y values out that are then allowed to fit into our f of x function. So working backwards a little bit, we can see that f of x needs to have all positive numbers going into it, or 0. So the y values that come out of our g of x, or green function, have to be positive. So all of these values here are possible, all the way until negative 2 on 3. So just to reiterate that, if we go from x is negative 2 on 3 to infinity for the g of x function, we get all positive values and 0 out. And those values can then fit inside of f of x, because that's the composite function, it's f of g of x. So they can fit inside of f of x, because we're allowed to put 0 and positive numbers inside there. So that means the domain of the composite function f of g of x is going to go from negative 2 on 3 all the way to infinity. So when we use that as our domain, when we put those x values into g, they give y values out that are positive or 0, which are then allowed into the function f, which has the rule the square root of x. And now with that information, we could actually have a go at sketching the graph of f of g of x down here. So that's x and y. And when we put negative 2 on 3 into g of x, we get 0 out. And putting 0 into f, we get the square root of 0 is 0. So it will go from this value here, and it will have a square root shaped graph, and it's going to have an endpoint at negative 2 on 3, 0. So with that graph in mind, we can see that the range of f of g of x is going to go from 0 to infinity. So that's the answer to part D of this question. Next, we're going to try something a little bit more complex. So we're going to still consider the function with the rule f of x equals the square root of x. But now we're going to have h of x equals x squared plus 2x minus 8. And for part E, we want to write down the rule for the composite function f of h of x. And we're going to do that in red. So once again, we're just going to quickly sketch the graphs of the functions that we're dealing with for this question. So on the first set of axes, I'm going to draw f of x, which is simply the square root of x, and it has a starting point or an ending point of 0, 0. And next up, we're going to sketch the graph of h of x, which we're going to do in purple. And just before we go and do that, we can factorize h of x so that we can find the x-intercept. So h of x can be written in factorized form as x plus 4 and x minus 2. So that means we're going to have an x-intercept at negative 4 and at positive 2, so it's going to look something like this. So that's going to be the function of h of x. And its value here is going to be negative 4, 0. And this x-intercept is going to be at 2, 0. And not that we need them, but this is 0, negative 8. And the turning point is at negative 1, negative 9. So now if we go back to part E and we want to write down the rule for the composite function f of h of x, we want to have f of, and then inside wherever there's x, we're going to put h of x, and that is going to equal f, the outer function is the square root function, so we're going to leave a big space for here because underneath that we're going to have h of x, and h of x's rule is x squared plus 2x minus 8. So that is the rule for the function f of h of x. Next up, we want to state the maximal domain for which f of h of x is defined. So thinking this through, we need to put x values into h that give positive or 0 out so that it can fit inside of the function f. So working backwards a little bit, the domain, which I'm just doing in yellow, for the rule of f of x is positive numbers and 0. So the y values that come out of h of x need to be positive or 0, which are these values here that I'm just doing in the highlighted area. And from the parts that we've highlighted on the second graph, we can see that the x values that we are interested, x is an element of, and it's negative infinity until negative 4, and we can include that value, union with 2 included to infinity not included. So that is the maximal domain for which the composite function f of h of x is defined. And now that we've done that, we could have a little go at attempting to sketch f of h of x. So we're going to draw another set of axes down here. So that's the y-axis and the x-axis. And this graph is going to exist from 2 to infinity. And when we plug 2 into that rule, we get 0, so the square root of 0 is 0. So at 2 down here, this is included, and then it starts to look like this graph, and that's 2, 0. And then the graph will also exist from negative infinity to negative 4. So at negative 4, somewhere around here, we're also going to have a similar shaped graph going in this direction, and that's going to be negative 4, 0. And now for this slide, we're going to think a little bit more about the range of a composite function. So finally, we're going to consider the functions with the rule f of x equals the square root of x, which hasn't changed yet, and we're going to do that in blue again. And now we're going to have p of x, which is equal to x squared plus 4, and I'm going to do that in orange. And the composite function this time is f of p of x, and we're going to continue to do that composite function in red. For part G, we're asked to find the maximal domain for which f of p of x is defined, and for part H, we're going to state the range of that composite function. So up next, we're going to do a few quick sketches of the graphs that we have under consideration. So first of all, which is what we've had the whole way through, is going to be the graph of f of x. So that is a graph with an endpoint at 0, 0, and it's a square root graph that looks like this. So we have 0, 0 here. And then next up, which we're going to do in orange, we're going to do the graph of p of x. And this graph is a parabola that's translated 4 units in the positive y direction. So it looks something like this, and it has a turning point here at 0, 4. And now we need to think about the maximal domain for which f of p of x is defined. So when we have a question like this, what we're really needing to do is find the x values that you can plug into p of x, which give y values that then could be subbed into f of x. So f of x has a domain, which we'll do in yellow again, as being 0 to infinity. And we can see that p of x gives out y values that are all greater than 4. So they can all fit inside the function f of x. So all these values here that we get coming out of p of x can all be substituted back into f of x. So what does this mean for the maximal domain for which p of f of x is defined? It means we can sub x values in that go from negative infinity to positive infinity, and all of them will give y values that can then be substituted into f of x. So the maximal domain is all real numbers, or we can write it from negative infinity to positive infinity. And now we need to state the range of the composite function f of p of x. So we're going to do a little sketch of this function below. So we're going to have y and x. And now the smallest y value that comes out of p of x is 4. And when we put 4 into f of x, the square root of 4 is 2. So if we just summarize our thinking for a moment, I'm going to put the x value of 0 into the function of p, which I'm going to represent with a orange box here with the letter p on. So that means we're going to do p of 0. And when we put 0 into p, we get 4 out. So we get the number that is 4 that comes out of there. And we're immediately going to substitute that into the function f, which is going to be a little box with the letter f written on it. And into f, we're going to put 4. And we know that f of 4 is the square root of 4, which gives a value out of 2. So on our graph of f of p of x, when we put 0 in for x, so x is 0 is just here. When we put 0 in, we get 2 out, so it's going to be that value there. And now every value that we put in on the positive and negative side of that are all going to give bigger y values, and we're going to get a function that looks a little bit like this. And that is the graph of f of p of x. And it had a turning point or a minimum point here at 0, 2. So with that in mind, and we've talked a lot about this now, but with that all in mind, the range of that graph we can see goes from 2 included until infinity. So that is the answer to part H of this question. So now we're just going to summarize what we know about composite functions. So composite functions contain multiple functions or multiple rules within a single function. So the composition involves substituting another function in where x would have originally been in a different function. So that's best expressed as the composition of f with g is FOG, but we don't use that notation very much. We use things like f of g of x or g of f of x, which you've seen a fair bit of in the previous slides. For f of g of x, the function g is applied first, followed by the function f. For a composite function f of g of x to exist, and this is really important, we need the range of the inner function, in this case g of x is the inner function, to be a subset or equal to the domain of the outer function. And as it's written, f is that outer function. So we can summarize that as being the range of the inner must be a subset or equal to the domain of the outer function. We know that we can restrict the domain of the inner function so that a composite function will exist. We know that the domain of the composite function is dependent on the domain of the inner function, and we can write that as the domain of f of g of x is equal to the domain of g of x, and sometimes, as we said above, it can be restricted. And finally, the range of the composite function is dependent on the range of the outer function. However, this is somewhat more tricky as it's also affected by the domain of the inner function. And the last few questions we did in this video were trying to emphasize that you really do need to consider the graphs of your original functions and the composite function so that you can get that domain and range correct.